Next, we talk about wireless transmission. In wireless transmission, three general range of frequencies are of interest in our discussion. The frequency in range is about 1 gigahertz. Gigahertz means 10 to the power 9 hertz to 440 gigahertz are referred to as microwave frequency. At these frequency, highly directional beam are possible and the microwave is quite suitable for point to point transmission. Microwave is also used for satellite communication. Frequency in the range of 30 megahertz to 1 gigahertz are suitable for the omnidirectional application. We refer to this range as a radio range. Another important frequency range for local application is infrared portion of the spectrum. This covers roughly from 3 into 10 to the power 11 to 2 into 10 to the power 14 hertz. Infrared is useful to local point to point and multi point application within confined area such as single row. For unguided media, transmission and reception are achieved by means of an antenna. Before looking at a specific categories of wireless transmission, we provide a brief introduction of antenna. Antenna can be defined as the electrical conductor or system of conductor that is used either for radiating electromagnetic energy or for collecting electromagnetic energy. For transmission of a signal, radio frequency electrical energy from the transmitter is converted into electromagnetic energy by the antenna and radiated into the surrounding environment such as atmosphere, space and water. For reception of a signal, electromagnetic energy impinging on the antenna is converted into radio frequency, electrical energy and fed into the receiver. In two-way communication, the same antenna can be and often is used for both transmission and reception. This is possible because any antenna transfer energy from the surrounding environment to its input receiver terminal with the same efficiency that it transfer energy from the output transmitter terminal into the surrounding environment. Assuming that the same frequency used in both direction, we put another way antenna characteristics are essential and the same whether an antenna is sending or receiving electromagnetic energy. The antenna will radiate power in all directions but typically does not perform equally well in all directions. A common way to characterize the performance of the antenna is the radiation pattern, which is a graphical representation of the radiation properties of the antenna as a function of space coordinates. The simplest pattern is produced by the equalized antenna known as isotropic antenna. An isotropic antenna is the antenna in space that radiate power in all the direction equally. The actual radiation pattern for the isotropic antenna is a sphere with the antenna at the center. Next antenna is called parabolic reflecting antenna. In parabolic reflecting antenna, an important type of antenna is a parabolic reflecting antenna which is used in terrestrial microwave and satellite application. A parabola is a locus of all the point equidistant from the fixed line and the fixed point, not on the line. The fixed point is called a focus and the fixed line is called a directrix, that is shown in figure. This is the focus and the directrix. If the parabola is revolved about its axis, the surface generated is called a parabolite. A cross sectional through the parabolite parallel to its axis form a parabola and a cross sectional perpendicular to the axis form a circle. Such surfaces are used in headlights, optical and radio telescopes and the microwave antenna because of the following property. If a source of electromagnetic energy or sound is placed at a focus of the parabolite and if the parabolite is a reflecting surface, then the wave will bounce back in line parallel to the axis of the parabolite. In figure 4.5b shown this effect in the cross section. In theory, this effect creates a parallel beam without dispersion. In practice, there will be some dispersion because of the source of energy must occupy more than one point. Larger the diameter of the antenna, the more tingly tightly directional is the beam. On reception, if incoming waves are parallel to the axis of the reflecting parabolite, the resulting signal will be co-centered at the focus. Next we talk about antenna gain. Antenna gain is a measure of directionality of the antenna. Antenna gain is defined as the power output in a particular direction compared to that produced in any direction by a perfect omnidirectional antenna, that is isotropic antenna. For example, if an antenna has a gain of 3 decibel, that antenna improves upon isotropic antenna in that direction by 3 decibel or a factor of 2. The increased power radiated in a given direction is at the expense of other direction. In effect, increased power is radiated in one direction by reducing the power radiated in another direction. It is important to note that antenna gain does not refer to obtaining more output power than input power, but rather to directionality. A concept related to that antenna gain is the effective area of the antenna. The effective area of the antenna is related to the physical size of the antenna and to its shape. The relationship between the antenna gain and effective area is G equals to 4 pi AE upon lambda square. In case of lambda, we can put C upon F. Here G is called antenna gain, AE is called effective area, F is the carrier frequency, C is the speed of light, that is 3 into 10 to the power 8 meter per second. Lambda is called the carrier wavelength. For example, the effective area of isotropic antenna is lambda square upon 4 pi, which is with the power gain of 1. The effective area of parabolic antenna with the face area of A is 0.56 A with the power gain of 7 A upon lambda square. Here there is example in which we simply find the wavelength. Next is called terrestrial microwave. Here the physical description is this: the most common type of microwave antenna is the parabolic dish. A typical size is about 3 meter in diameter. The antenna is fixed rigidly and focus a narrow beam to achieve line of sight transmission to the receiving antenna. Microwave antenna are usually located at substantial height above the ground level to extend the range between the antenna and to the able to transmit over the intervening obstacles. To achieve long distance antenna, a series of microwave relay tower is used and the point to point microwave links are strung together over the desired distance. Applications: the primary use of terrestrial microwave system is in long haul telecommunication surveys as an alternative to coaxial cable or optical fiber. The microwave facility requires a far fewer amplifiers or repeaters than coaxial cable over the same distance, but require line of sight transmission. Microwave is commonly used for both voice and television transmission. Another increasingly common use of microwave is for short point-to-point link between buildings. This can be used for closed circuit TV or as a data link between local area network. Short haul microwave can also be used for the so-called bypass application. A business can establish a microwave link to a long distance telecommunication facility in the same city, bypassing the long telephone company. Another important use of microwave is in cellular system, which we will examine in chapter 14. Here there are typical digital microwave performance having a band for the bandwidth of 2 gigahertz to bandwidth in megahertz and the data rate megabit per second. Transmission characteristics: microwave transmission covers a substantial portion of the electromagnetic spectrum. The common frequency used for transmission is in the range of 1 to 40 gigahertz. The higher the frequency used, the higher is the potential bandwidth and therefore the higher the potential data rate. Table 4.6 indicate bandwidth and data rate for the same typical system. As with the transmission system, the main source of loss is attenuation. For microwave and radio frequency, the loss can be expressed as L equals to 10 log 4 pi d upon lambda whole square decibel, where d is the distance and the lambda is the wavelength in the same unit. Thus, loss varies as the square root of the distance. In contrast, for twisted pair and coaxial cable, loss varies exponentially with distance linear decibel. Thus, repeaters or amplifiers may be placed farther apart from the microwave system, that is 10 to 100 km is typical. Attenuation is increased with rainfall. The effects of rainfall become especially noticeable noticeable above 10 gigahertz. Another source of impairment is interference. Most of the growing popularity of microwave transmission area, thus the assignment of frequency band is strictly regulated. The most common band for long haul telecommunication are the 4 gigahertz to 6 gigahertz band, which increase congestion at these frequencies, and the 11 gigahertz band is now coming into use. The 12 gigahertz band is used as a component of cable TV system. Microwave links are used to provide TV signals to locate CATV installation. The signal is then distributed to individual subscriber via coaxial cable. Higher frequency microwave is being used for the short point-to-point link between buildings. Typically, the 22 gigahertz band is used. The higher microwave frequency are less useful for long distance because of increased attenuation, but are quite adequate for short distance. In addition, at the high frequency, the antennas are smaller and cheaper. Next is called satellite microwave. In this, the physical description, a communication satellite is in effect a microwave relay station. It is used to link two or more ground-based microwave transmitter receiver known as earth station or ground station. The satellite receives transmission on one frequency band, that is uplink, amplify or repeat the signal, and transmit it to another frequency downlink. A single orbiting satellite will operate on the number of frequency band called transponder channel or simply transponder. As shown in figure 4.6, it depicts in a general way two common configuration for satellite communication. In the first, the satellite is being used to provide a point-to-point link between two distant ground-based antenna. In the second, the satellite provides communication between two ground-based transmitter and the number of ground-based receiver. For a communication satellite to function effectively, it is generally required that it remains stationary with respect to the position over the earth. Otherwise, it would not be within the line of sight of its area of its earth station at all time. To remain stationary, a satellite must have a period of rotation equal to the earth period of the rotation. This match occur at a height of 35,863 km at the equator. So this is a point-to-point link. And second is called broadcast link. There are the two satellite communication configuration. Two satellite being using the same frequency band, it close enough together will interfere with each other. To avoid this, current standard required a 4-degree spacing angular displacement as measured from the earth in the 4 to 6 gigahertz band and a 3-degree spacing at 12 to 14 gigahertz. Thus, the number of possible satellites is quite limited. Application: the following are among the most important application for satellites. For example, television distribution, long distance telephone transmission, private business network, global positioning. Because of their broadcast nature, satellites are well suited to television distribution and are being used extensively in United States and throughout the world for this purpose. In its traditional use, a network provides programming from a central location. Programs are transmitted to the satellite and then broadcast down to a number of stations which then distribute the program to individual viewer. One network, the Public Broadcasting Service (PBS), distributes its television programming almost exclusively by the use of satellite channel. Other commercial networks also make substantial use of satellites, and cable television system are receiving the ever increasing proportion of their programming from satellites. The most recent application of satellite technology to television distribution is the direct broadcast satellite (DBS), in which satellite video signals are transmitted directly to the home user. The decreased cost and size of the receiving antenna have made DBS economically feasible. Satellite transmission is also used for point-to-point trunks between telephone exchange offices and public telephone network. It is optimum medium to high usage international trunks and is competitive with terrestrial system for many long distance international links. There are the number of business data applications for satellite. The satellite provider can can divide the total capacity into the number of channels and lease these channels to individual business user. A user equipped with the antenna at a number of sites can use a satellite channel for a private network. Traditionally, such applications have been quite expensive and limited to large organizations with high volume requirement. A recent development is the very small aperture terminal VSAT system, which provide a low cost alternative. As shown in figure depicts a typical VSAT configuration. A number of subscriber stations are equipped with the low cost VSAT application VSAT antenna using some discipline. These satellites share satellite transmission capacity for the transmission to the hub station. A hub station can exchange messages with each of the subscriber and can relay messages between the subscriber. The final application of satellites which has become pervasive is worth to note. The Navstar Global Position System, or GPS for short, consisting of 3 segments or components. Constellation of satellite, currently 27, orbiting about 20,000 km above the Earth's surface, which transmit ranging signal on 2 frequencies in the microwave part of the radio spectrum. This is a typical VSAT configuration. The control segment which maintains GPS through the system of ground monitor satellite station satellite upload facility. Your user receivers both civil or military. Each satellite transmits a unique digital code sequence of 1s and 0 precisely timing by the atomic clock, which is picked up by the GPS receiving antenna and the match with the same code sequence generated inside the receiver. By lining up or matching the signal, the receiver determines how long it takes the signal to travel from the satellite to the receiver. These timing measurements are converted to distance using the speed of light, measuring distance of 2, 4 or more satellites simultaneously and knowing the exact location of satellite, including in the signal transmitted by the satellite. The receiver can determine its latitude, longitude and height, while at the same time synchronizing its clock with the GPS time, which also make the receiver a precise time piece. Transmission characteristic: the optimal frequency range of the satellite transmission is the range of 1 to 10 GHz. Below 1 GHz, there is significant noise from natural sources, including galactic, solar, atmospheric noise, human-made interference from various electronic devices. Above 10 GHz, the signal is severely attenuated by atmospheric absorption and precipitation. Most satellites providing point-to-point service today use as a frequency band within the range of 5.925 to 6.425 GHz for transmission from Earth to satellite uplink, and the bandwidth in the range of 3.7 to 4.2 GHz for the transmission of satellite to Earth downlink. This combination is referred to as the 4-6 GHz band. Note that the uplink downlink frequency differ. For continuous operation without interference, the satellite cannot transmit and receive the same frequency. Thus, signal received from the ground station on the one frequency must be transmitted back to another. The 4/6 GHz is within the optimum zone of 1 to 10 GHz but has become saturated. Other frequencies in that range are unavailable because of the source of the interference operating at these frequencies, usually terrestrial microwave. Therefore, the 12 to 14 GHz band has been developed, uplink 14 to 14.1 GHz, downlink 11.7 to 12.2 GHz. At this frequency band, the attenuation problem must be overcome. However, smaller and cheaper earth station receiver can be used. It is anticipated that the band will also saturate and the use of projected from the 20-30 GHz, uplink 27.5 to 30 GHz, downlink 17.7 to 20.2 GHz. This band experiences even greater attenuation problems but will allow greater bandwidth 2500 MHz versus 500 MHz and use smaller and cheaper receivers. Several properties of satellite communication show is noted. First, because of the long distance involved, there is a propagation delay of about quarter second from transmitter from one station to the reception by another station. This delay is noticeable in ordinary telephone conversation. It also introduced problem in the area of the error control and the flow control, which we discussed in the later chapter. Second, satellite microwaves inherently broadcast factory. Many satellite can transmit to satellite, and the transmission from one satellite can be achieved by many stations. Next is called broadcast radio. In physical description, the principal difference between broadcast radio and the microwave is that The former is omnidirectional and the latter is directional. Thus, the broadcast radio does not require dish-shaped antenna and the antenna need not be rigidly mounted to the precise alignment. The applications are: radio is a general term used to encompass frequencies in the range of 3 kHz to 300 GHz. We are using the informal term broadcast radio to cover the VHF and the part of UHF band 30 MHz to 1 GHz. This range covers FM radio and the UHF and VHF televisions. This range is also used for a number of data networking applications. Transmission characteristics: the range 30 MHz to 1 GHz is effective one for broadcast communication. Unlike the case for lower frequency electromagnetic waves, the ionosphere is transparent to radio waves above 30 MHz. Thus, transmission is limited to the line of sight and distance transmitter will not interfere with each other due to the reflection from the atmosphere. Unlike the higher frequencies from the micro region, the broadcast radio waves are less sensitive to the attenuation from the rainfall. As with microwave, the amount of attenuation due to the distance obey an equation, that is 10 log 4 pi d lambda whole square decibel. Because of the longer wavelength, radio wave suffers relatively less attenuation. The primary source of impairment for broadcast radio waves is multi-part interference. Reflection from land, water, natural or human-made objects can create multiple paths between antennas. This effect is frequently evident when TV reception displays multiple images as an airplane passes by. Next is called infrared. Infrared communication is achieved using transmitter receiver, that is called transceiver, that modulate non-coherent infrared light. The transceiver must be within the line of sight of each other, either directly or via reflection from the light colored surface such as the ceiling of the room. One important difference between infrared and the micro transmission is that the former does not penetrate walls. Thus, the security interference problems encountered in the microwave system are not present. Furthermore, there is no frequency allocation issue with infrared because no license required. In wireless communication, the signal radiation from the antenna travels along one of the three routes: ground waves, sky waves or line of sight. In table 4.7 show in which frequency range each predominates. Here we are also exclusively concerned with line of sight communication, but a short overview of each mode is given in section. First is called ground wave propagation. Ground wave propagation, as shown in figure 4.8a, this is a ground wave propagation that is below 2 MHz. More or less follow the counter of the earth and can propagate considerable distance well over the visual horizon. This effect is found in the frequency up to about 2 MHz. Several factors account for the tendency of electromagnetic waves in this frequency band to follow the earth's curvature. One factor is that the electromagnetic wave induces current in the earth's surface, the result of which is to slow the wavefront near the earth, causing the wavefront to tilt downward and hence follow the earth curvature. Another factor is diffraction, which is the phenomena having to do with the behavior of the electromagnetic wave in the presence of obstacles. Electromagnetic waves in the frequency range are scattered by the atmosphere in such a way that they do not penetrate the upper atmosphere. The best known example of the ground wave communication is AM radio. Skywave propagation is used to amateur radio, CB radio and the international broadcasts such as BBC and the Voice of America. With skywave propagation, a signal from the earth-based antenna reflected from the ionized layer of the upper atmosphere, that is called ionosphere, back down to the earth. Although it appears the wave is reflected from the ionosphere as if the atmosphere edges of the ionosphere with a hard reflecting surface, the effect is in fact caused the refraction. The refraction is described subsequently. The skywave signal can travel through the number of hopes bouncing back and forth between the ionosphere and the atmosphere, earth's surface, that is shown in figure B. This is called skywave propagation. Here there is a reflection through the ionosphere. With this propagation mode, a signal can be picked up thousands of kilometers from transmission. Next is called line of sight propagation. Above 30 MHz near ground wave or skywave propagation mode operate, and communication must be by line of sight, that is shown in figure C. This is a line of sight propagation. For satellite communication, a signal above 30 MHz is not reflected by the ionosphere, and therefore the signal can be transmitted between the earth station and the satellite overhead that is not beyond the horizon. For ground based communication, the transmitter receiving antenna must be within the effector line of sight of each other. The term effector is used because if microwaves are bent or refracted by the atmosphere, the amount or even the direction of the bend depends on the condition, but generally microwaves are bent with the curvature of the earth and will be therefore propagate farther from the optical line of sight. Now we talk about refraction. Before proceeding, a brief discussion of refractions. Refraction occurs because of the velocity of the electromagnetic wave is the function of the density of the medium through which it travels. In the vacuum, electromagnetic waves such as light or radio waves travel approximately 310 meters per second. This is the constant c, commonly referred to the speed of light, but actually referring to the speed of light in vacuum. In air, water, glass and other transparent or partially transparent medium, the electromagnetic wave travels at speed less than c. When the electromagnetic wave moves from a medium from one density to the medium of another density, its speed changes. The effect is to cause one-time bending of the distance to the wave at the boundary between two media. Moving from the less dense to the more dense medium, the wave will bend toward the more dense medium. The phenomena is partially immersed stick in water, easily observed by the partially immersed stick in water. The index of refraction or refracting index of one medium related to another is the sine of the angle in incident divided by the sine of the angle of refraction. Index of refraction also equal to the ratio of the respective velocity in the two media. The absolute index of refraction of the media is calculated in composition with that of the vacuum. Refractive index vary with the wavelength, so that the refractive effect differ from signals with different wavelengths. Although an abrupt one-time change in direction occurs as the signal moves from one medium to another, a continuous gradual bending of the signal will occur if it is moving through a medium in which the index of refraction gradually changes. Under normal propagation condition, the refractive index of the atmosphere decreases with the height, so that the radio wave travels more slowly near the ground than at higher altitude. The result is a slightly bending of the radio wave toward the earth. Optical and radio line of sight. With no intervening obstacle, the optical line of sight can be expressed as d equals to 3.57 under root h, where d is the distance between the antenna and the horizon in kilometer and h is the antenna height in meter. The effective or radio line of sight of the horizon is expressed by d is equal to 3.57 into kh. Here k is called adjustment factor to account for the refraction. A good rule of thumb is k equals to 4 by 3, thus the maximum distance between two antenna for lines of sight propagation is 3.57 whole bracket under root k h1 plus k h2, where h and h2 are the heights of the two antenna. So this is a formula in which we can use for in this example. Next is called line of sight transmission. In this section, we discuss various transmission impairment common to both guided and wireless transmission. In this section, we extend the discussion to examine some of the impairments specified to wireless line of sight transmission. Free space loss. For any type of loss, wireless communication, the signal disperses with distance. Therefore, the antenna with a fixed area will receive less signal power the farther it is from the transmitting antenna. For satellite communication, this is the primary mode of the signal loss. Even if no other source or attenuation impairment are assumed, a transmitted signal attenuates over distance between the signal is being separated over a larger and larger area. This form of attenuation is known as the free space loss, which can be expressed in terms of the ratio of the radiated power Pt to the power Pr received by the antenna, or in decibel by taking 10 times the log of that ratio. For ideal isotropic antenna, the free space loss is Pt upon Pr equals to 4 pi d whole square upon lambda square equals to 4 pi f d whole square upon c square. where PT is the signal power at the transmitting antenna, PR is the signal power at the receiving antenna, lambda is the carrier wavelength, D is the propagation distance between antenna, C is the speed of light, 3 × 10⁸ meter per second, where D and lambda are the same unit, that is meter. This can be expressed in terms of decibel, that is 10 log PT upon PR. So after this, after solving, we get L decibel equals to 20 log F plus 20 log D minus 147.56 decibel, as shown in figure 4.7, which illustrates the free space loss equation. This is a loss of decibel with respect to distance. Now, atmospheric absorption. In addition to losses between transmitting and receiving antenna in atmosphere, there is the atmosphere absorption. Water vapors and oxygen contribute most of the attenuation. The peak attenuation occurs in the vicinity of 22 GHz due to the water vapor. At frequency below 15 GHz, the attenuation is less. The presence of oxygen results in an absorption peak in the vicinity of 60 GHz, but contribute less at frequency below 30 GHz. Rain and fog, suspended water droplet cause scattering of radio waves that result in the attenuation. In this context, the term scattering refers to the production of the waves of charge, change direction of frequency when radio waves encounter matter. This can be the major cause of signal loss. Thus, in the area of significant precipitation, either path loss have to be kept short or low frequency bands should be used. Next is called multipath. In wireless facility where there is a relatively free choice of where antenna are to be located, they can be placed so that there is no nearby interfacing obstacle. There is a direct line of sight path from the transmitter to receiver. This is generally the case for many satellite facilities and for point microwave. In other cases such as mobile telephony, there is obstacle abundance. The signal can be reflected by such obstacles so that the multiple copies of the signal with varying delays can be received. In fact, in extreme case there may be no direct signals. Depending on difference in the path length of the direct or reflective wave, the composite signal can be either large or smaller than the direct signal. Reinforcement and the cancellation of the signal resulting from the signal follow multiple path can be controlled by the communication between fixed well-suited antenna and between the satellites and fixed ground station. One exception is when the path goes across the water, where the wind keep the reflective surface on the water in motion. For mobile telephony and communication of antenna, there are no well-suited multipath consideration can be paramount. In figure 4.11 illustrate the general terms, the type of multipath interference typically in terrestrial, fixed, microwave and the mobile communication. For fixed microwave, in addition to the direct line of sight, the signal may follow the curved path through the atmosphere. Due to the refraction, the signal may also reflect from the ground. For mobile communication, structure and topography feature provide reflecting. So this is the microwave line of sight, and this is example of multipath interference. Next is called refraction. Radio waves are refracted or bent by when they propagate through the atmosphere. The refraction is caused by changing the speed of the signal with altitude or by other spatial change in the atmosphere condition. Normally the speed of the signal increases with altitude, causing radio waves to bend downwards. However, on occasion weather condition may lead to the variation in speed. With height they differ significantly from the typical variation. This may result in the situation in which only the fraction or no part of the line of sight reaches the receiving antenna.